And for this afternoon session, after each presentation, the presentations will be about 20 minutes. I'll have 5 minutes for questions. And I ask if you could fill out a green speaker card and write down your question. I'll take those first, then I'll take those from the web, and then I'll take audience questions randomly. So, okay, perfect. Here you go.
So, am I starting?
You're starting.
Okay. Well,
Yourself, please. I didn't.
I certainly will. My name is Yoram Cohen, and I'm at the School of Engineering at UCLA at the Chemical and Biomolecular Engineering Department, and also a faculty at the Institute of the Environment and Sustainability. And it's a pleasure to be here today to share with you some of our thoughts, my thoughts. I'm going to try and be a little bit provocative, today, and I can afford to do that because it's my birthday. So I don't care if you give me a hard time. And what I intend to do here is to go over certain ideas. There was quite a bit in terms of discussion of technology here, but I want to bring in a number of key elements that are really, really important for remote communities or small communities in terms of operability, and I'll touch upon those ideas. So you've seen this map in various forms. The main point that I want to make here is that if you look at it, you'll see that you have sites distributed all over. And this is just for the case where you're looking at different wells where contamination has been reported, and we've all seen that. And looks like my laser is not working on that screen, but basically the point is that there is diversity of sites. Now, what do I mean by diversity? It's diversity with respect to treatment needs, diversity with respect to the use capacity, diversity with respect to accessibility of those sites, and whatever infrastructure there is. So basically what that tells you is that you're not going to find one solution for all of those sites, and you've heard that over and over again. So what are the main issues that we're confronted with when we are trying to develop a solution? One is that there isn't enough data. Although there have been quite a bit of monitoring, what you'll find is that many of those locations, water quality changes over time. So whatever you do today may not be the same a week, a month, a few months away. And I'm not saying it just because I'd like you to believe me. I'm saying it because we've actually done monitoring in the San Joaquin Valley, over the years, in fact, to find that out in certain locations where you have a community that is near a farmland. When you have irrigation, you'll see changes in water quality. So monitoring is an issue because it's not continuous in many of those locations, and we have the challenge of small systems. So in small systems, treatment and management of residuals is important to consider. So I'll just summarize in a slightly different way in terms of the challenges so that you can see why I'm going where I'm going with respect to the acceptability of distributed water systems. One is that often there is a lack of resources and capital and infrastructure. Not very much sort of the forte of an engineer like myself, but I do recognize the importance of this. Water demand can be very sensitive to population dynamics, and this we have to recognize because what you design for a location that may require that has 8 or 10 connections or so many houses, in a few years that may change. So your system design may totally have to be reconfigured. So that means that systems that we design have to be reconfigurable. I imagine in a small community, if you have 10 homes and half of them are on vacation, then all of a sudden your use capacity drops by 50%. So you have to be aware of that if you use biological treatment, for example. That can be an issue. There is also a challenge with respect to unique site-specific conditions, which I mentioned already. But a key is a key in terms of operation is that with a small system, you're not going to have an operator 24/7. So that means that you have to think differently in terms of how the system will operate, how autonomous they're going to be, and how adaptive they're going to be to changing conditions. Now, I put the last one, you see technical, and I put legal just to satisfy my wife because she's an attorney. So, you know, she said, where's the legal part in what you're talking about? I have no idea. So, but in any event, I think many of you will recognize that there are issues with regulatory issues that need to be considered, and how would a small community cope with it relative to a case where you have a centralized plant can be quite different. So you've seen part of this in the earlier talk today, but this is from the Davis study, but I adjusted it a little bit just to make a couple of points. You've heard about ion exchange, and I added to that adsorption, because ion exchange is specific to polar materials, but adsorption can be added on to remove also non-polar materials as well, although activated carbon may remove both to some extent. Now, you heard about RO, or what I would call membrane-type filtration, whether it's RO nanofiltration. You heard about EDR, or electrodialysis, or electrodialysis reversal, biological denitrification, and chemical. So I'm just going to focus on a couple of points. Right here in terms of residuals, and you notice that I didn't call it waste, and I call it residuals because it's important, because sometimes what is waste to one party may in fact be a resource for another. So in the case of ion exchange, we already heard that we have high salinity brine. In the case of RO, of course, you've got the concentrate, and the same is true that there will be some in electrodialysis. You'll have sludge and biosolids that can be a challenge at times to handle, and the same with chemical denitrification. In terms of operability, I indicated in here start and stop. Well, that's important because in a small community, you can't assume that you'll always have a very, very steady operation for those systems. So most of the systems have fast start and fast stop. In the case of biological denitrification, it's a little bit different because they're slow to start. So we've heard that there's going to be a lot of effort put into understanding just what is this period under whatever the different conditions are. Now, in terms of the water recovery, and that is important, you heard that ion exchange has a high recovery. On the other end, if you look at RO or NF, typically 75, 85, but we can push it to 95, and I'll show you an example. Electrodialysis is high, and of course biological denitrification is nearly 100%. But the main issue, since we're talking about drinking water and water of high quality, is the barrier protection. We talk about nitrates and nitrates as if this is the only thing that there is in that water. I've never seen water that only has nitrates. Okay? I've never seen water that has only one component. Okay? Water is a very complex mixture. So when you look at the different methods, ion exchange, you know, does it provide barrier protection? The answer is no, because it will not protect you with respect to organics, okay, for example. Maybe some polar organics, but it will not protect you against many pesticides. Can you add adsorption? Sure, you can add adsorption, but now you have a train, okay, of different unit operations. The only one out of all of those in here that really provides the multiple barrier protection is RO. For better or for worse, simply because this is, and actually is, a barrier. And in terms of ions, RO will reject 99.97%. In terms of nitrates, 85 to 95% that will be rejected. So, which one do you use? Of course, it depends on what the water quality will be and what is it that you can afford in terms of the barrier protection. Or not what you can afford, but what is it that you need in terms of the barrier protection. So, here we go to the case that I'm trying to make here is for a paradigm shift. That means that if we have systems, and the ones that I will focus on primarily is basically membrane-based and ion exchange, because they can be complementary in many ways. In order to make them work, we have to start thinking differently, and we have to start thinking in terms of engineering design that is a scale down rather than a scale up. we have distributed systems, and so if they're distributed, it also means that we have a challenge now that those systems have to be robust, self-adaptive. You don't have an operator that can be there 24/7, so they have to be autonomous. Now, what does that mean? When I say they have to be autonomous, I don't mean you simply flip the switch and the pump is running. Okay? But what it means is that if the concentration of nitrates is now reaching a point where you might have a spike, or that you have reached the exhaustion of the ion exchange resin, then you need to know in advance. Well, how do you know in advance? We can implement model-based control by understanding how the ion exchange system works and actually predict in advance what might happen using various sensors that tell us, have we reached that breakthrough point in the ion exchange resin? In the case of RO, we heard that there is an issue that maybe there can be mineral scale. Well, we've run system in the San Joaquin Valley up to 85, 90% recovery in the worst conditions without mineral scale. Why? Because we monitor the system with respect to composition. We have mineral scale detector that tells us you're about to reach that condition, back off. And the system does that automatically by changing the recovery so that you're not in the danger zone. So that is what I mean by autonomous operation. But autonomous alone is not enough. The system has to be robust so it doesn't go into a fault. So I used, perhaps a fancy term that we use in control, which basically fault-tolerant operation. So we have what we call fault-tolerant operation and isolation, which means that we know a fault is about to occur, but we also need to know what's happening in the system, which sensor is about to fail, which component, which valve is not operating properly. So we have to have detailed models of the system that allows us to do that. And you can do part of it locally with the system, but some of it has to be done off-site, which means that we, in some cases, we stream data to centralized servers where we do that. So that brings me to the last part, which is infrastructure for centralized monitoring and really operation and support of such systems, or to use the fancy word, cyber infrastructure. NSF, the National Science Foundation, loves this term. Okay? They're putting a lot of money into cyber infrastructure. So we, in fact, have a program on cyber infrastructure for distributed water systems, and I'll show you a few of those systems in a minute. So I'm going to skip this because I've already talked about it quite a bit, but now I want to go into just giving you a sense of cost in a minute. And here is where perhaps I differ with some estimates that have been done, is in order to estimate what a remote community may need, or a typical household, is not easy to do, because there are some communities that use a lot of water for irrigation if it's a farmland, and others less. But if you look in California and you look at water use per capita or per household, as you see in here, Tulare Lake, the San Joaquin Valley across, and the Central Coast, you see that there is quite a variability in terms of the amount of water that is used per capita, and I assume, and then convert it here to per household, you see that there's quite a variability. If you look at California, on the average, it's about 387 gallons per day. I don't use that much in our house. We are 4 people, 2 cats, and I don't think that we use more than about 200 gallons a day, if anything. We have gray water treatment system project in a home in West LA, and with all the activities there, they use about 100 gallons per day, and roughly about 50% is indoor-outdoor, so it's about 200. So we've actually monitored that with the Department of Water Resources. Now, the interesting part is that it's split roughly 50-50, as you can see, between indoor and outdoor, but the interesting part is that less than 9%, or let's say 10% or less, is used for drinking. So I'm not a policymaker, so I'm not going to get into what the implications of this, but you can immediately see what it means in terms of the quality of water that we are trying to arrive at. In other words, what is the water being used for, and therefore what is the level of quality that is required. Now, having said that, I've took the California average plus 30%. I said, let me just bump it up a little bit. And I've made the a daring assumption that there is one connection, per house. Okay, so I don't know if I'm overestimating or underestimating. So think about it as one connection is one house, 50 connections, 50 homes. And if you go according to this, it means that for 50 connections, you need 25 gallons per day. And that's at 503 gallons per day usage, which is significantly more than most people would use, at least in the urban environments. So we need to think about what those systems are being used, for. Does it make sense to remove nitrates to such a level to drinking water if it's going to be used at a level of 50% for irrigation? I know you didn't expect that from me because you expected just, technical talk. But I think that doing technology without understanding, those issues is, can be problematic. So let's look at the systems, and then I will show you costs, just so that we can get a sense of the size. One of the speakers before me have already alluded to the fact that we can have point of use systems, which you see here on my right. Yeah, your right. I had to verify. So this is a system by GE, which will produce 10 to 20 gallons per day, and this is using using activated carbon and also RO system. On the left, you see one of our small systems, which is again, it has adsorption, filtration, media filters, and RO, and it will produce about 5,000 to 8,000 gallons per day in terms of product. So it gives you a sense of the size, right? It's a system that it's almost small enough to put in your kitchen, if you have a large kitchen. Below, you see a system which we call the COM2RO, which stands for Compact Second Generation RO. And that system, in fact, is one that uses ultrafiltration system, microfiltration, adsorption, and then RO that you see in here. You're actually seeing it here in an industrial setting. It's actually treating water from cooling towers at a power generation plant. So it gives you a sense of the size when we talk about small, large. 46,000 gallons a day is not that small. Okay? If it's only for drinking, the average person is supposed to drink 2 liters per day or half a gallon per day. So we're looking at almost 100,000 people. Okay, in here. Of course, if we fill our swimming pools, that's a different story. All right, so let's look at what would be a system. I just took this as an example. And because I am an academic and because it's my birthday, I didn't pay attention to what CDPH said. And so I didn't follow their guidelines. So I hope that they will indulge me on this specific and very, very happy day. So I took source water and I said 100 ppm of contaminant, of nitrate, 750 ppm or milligrams per liter of total dissolved solids in terms of salts. System capacity for 50 connections would need to be about 25,000 gallons per day, assuming 503 gallons per day usage. And we're talking about nitrates removal would be about 85 to 95% for such system. So if you look at the capital costs and you amortize that, and again, I did a high estimate, in here, just to give you a sense. In terms of electricity and whatever chemicals might be needed, service fee, again, you see that it's a huge range. And why is it such a huge range? Because it is difficult to say where such a system would be in terms of infrastructure. So I just took the liberty of expanding that range. So what you see in terms of a treatment cost at the end, you're talking about $40 to $60 per month per connection, or in this case, it's a household. Now, That is if you produce water that is essentially not just drinking water, but if you use RO, it'll be, very, very high quality water. And it'll be way below the MCL. So the question is, do you really need to do that? So if I take this water and, for example, and I blend it, in fact, I can decrease the system capacity by 50%, for example, if I operate at even just 50% recovery. But, one has to optimize that. So one can reduce the cost significantly. On the other hand, in terms of treatment costs, it's the same story. We increase the concentration in the concentrate from those systems, but if you then blend that, and now you have the choice, if the system is revving up and you're producing more water than you need, you can blend it, back with the concentrate. Of course, you're wasting money, in this way. But if it's a regulatory burden that you must meet, then that's what you do. On the other hand, you can take that water, the concentrate, and you can blend it with the source water, okay, and reduce that. Now, of course, I probably step on a landmine, right now, okay? But what I'm saying is that there are various options in terms of the operation that need to be considered. So, just to give you an example of what an actual system, would look like at that, roughly at that size. It's actually larger. This is a system that we have that incorporates MF, UF, RO provisions for ion exchange and adsorption, disinfection capabilities. It's in a 40-foot ISO container. It's actually currently under construction, and it's for a project specifically to deal with agricultural water. And it's a system that will be deployed at the fourth quarter towards the, if all works well, and everybody works really hard, at the end of the fourth quarter of 2013. And it will operate at Panoche, at Red Rock Ranch, Tulare Lake. Red Rock Ranch specifically, there are also technologies there for handling of concentrate. So this system would be integrated with such approaches that use primarily evaporative type methods. So that particular system is on a trailer, and it's reconfigurable to match treatment needs. Is fully automated, self-adaptive, as I mentioned before, and controlled from afar. And I won't go into the details of all the monitoring that has gone into that system. And when I talk about reconfigurable, it's very important, because even if you just focus on RO can be done at 1 stage, 2 stages, or if you need very high purity water, it has to be done as a 2-pass, which means that you take the water that you produce in the first stage and then you treat it in a secondary RO. So, how much time do I have? None. Okay. All right, that's fine. We're at the end here. I just wanted to summarize to you concentrate residual management costs so that you kind of put it in perspective. Evaporative ponds, solar ponds, and by evaporative ponds, I don't mean just exposed to the sun. You actually have spray, well injection, and back to the sewer. So you see that the costs can be quite different. And it depends on the location, and that's why it's hard to pin it down and say this is going to be the cost. So you need to look at it on a site-by-site basis. And finally, to recognize that even if you have those distributed systems and they have a concentrate that needs to be managed, one can take that concentrate that now, if it's an RO, for example, it'll have a high nitrates. You can have a satellite treatment plant that will be biological treatment that would then be used to treat the concentrate from all those locations, because biological treatment will require a lot more in terms of careful operability than a membrane-based system. So a lot of thoughts, a lot of engineering that can go into it, and I'm just going to just show you some slides. Here is a system that I showed before. We've been operating for 2 years, actually, also with seawater desal at a secret base at Port Wanimi that you can only see from Google Earth, okay, right here, as you can see it, and a system that provides 18,000 gallons per day. And I'll finish here and just say I hope that in this whirlwind talk I've convinced you that there are many issues to consider with respect to to monitoring, to control, fault detection in such system. That disposal or management is a key element, but it can also be incorporated with the actual operability of such systems. And if we can get the cyber infrastructure for distributed water systems, then it's a whole new paradigm for a distributed water district, if you will. Thank you.
Thank you, Dr. Cohen. We are running a little bit long, but Dr. Cohen will not be around tomorrow, so I'll take one question right now.
Don't be afraid.
It's his birthday. No? Okay. Thank you very much. Okay, while we're loading the next one. So next, we have Microvibe Biotech, Ali Dori, biotechnology for treatment of nitrate in water. Thank you.
Good afternoon. My name is Ali Dori. I'm from Microvi Biotech. I am Director of Business Development at Microvi. I've been with the company for, we're actually a young company, but I've been with them for about 5 years now. And it's kind of a different approach to biological treatment. So what I'll do is I'll try to go through the slides, and usually I get a lot of questions, so I'll leave some time for questions at the end. But essentially it's a novel biotechnology for treatment of nitrate in water. Just a brief outline. I'll talk about who Microvi is, what we do, how long we've been around, talk a little bit about the technology itself, go through some example installations and case studies, and then leave some time for Q&A. So Microvi is a California-based company that was started in 2008 by Dr. Fatima Shirazi. We're currently commercializing some clean and sustainable technologies. We've got kind of a transformative technology, we like to call it, that treats a wide range of pollutants in water and wastewater, and we're also active in fermentation processes. From a nitrate drinking water perspective, we're currently partnering with Sunny Slope Water Company in Pasadena, California, to conduct the challenge testing for conditional acceptance of our product by CDPH for drinking water. We anticipate beginning here in a couple weeks. A novel biotechnology for nitrate treatment. I'll kind of run through this slide, but the key takeaway from this slide is that you've got water treatment typically falls into 3 basic categories. You've got biological, physical, and chemical. Physical and chemical treatments, the big downside is you're always producing a secondary waste stream that you've got to deal with. Biology, in my opinion, has the most potential. Unfortunately, we're working on trying to optimize operation of biological systems to make them much more efficient and to kind of get them to do what we want biology to do for us. These are just some of the biological systems today. The biggest downfalls is typically also associated with operational costs. Their footprint can be higher, and I'll kind of talk about some of the disadvantages and how we've kind of gone about addressing some of those disadvantages. Essentially, the coin term that we use is called micro-niche engineering. And where I say we differ from some of the other biological systems is micro-niche engineering is the concept of we focus on the microenvironment of an organism. So for example, if I've got an organism in soil, I try to mimic the environment in which it lives in the natural environment, in a kind of in a bioreactor. The only way to do that is to develop what we call it's kind of like a house essentially for these organisms on a micro level inside of a large reactor. Most biological systems today, it is extremely important, and we do pay attention to it, but they focus on the macro environment, which is the overall reactor design. Is it a packed bed? Is it a fluidized bed? What kind of pH is going in, temperature and whatnot. What we've done is we've tried to take that a step further and incorporate those along with trying to essentially create a niche environment for organisms inside of a reactor on a more micro level scale. So the technology, I think Eugene kind of touched on this, but essentially you would take what we call it's our biocatalyst that are inoculated, or they essentially have housed billions of organisms inside of them, specific to do a kind of a specific job or an application. You can essentially put it inside of a reactor. You can have a packed bed, fluidized bed. So you've got quite a variance when it comes to reactor design. And essentially you've got polluted water going in. It travels through these biocatalysts, it gets degraded, and clean water comes out. Obviously there's a need for an electron donor, and you've got some of CDPH's requirements such as filtration and chlorination that will be needed as well. Some of the results that, we're a younger company, but based on, and I'll walk through some of the studies that we've done so far, but the startup time is extremely rapid. Just to give an example, for nitrate, what we do is we identify a handful of organisms in nature that are known to denitrify. And then what we do is we take these organisms and we mass produce it in a fermentation type vessel at large scale. We then take that pure culture or that biomass and we run it through a manufacturing process where we then essentially we house them inside of a biocatalyst. And these biocatalysts they're about 3 to 5 millimeters, and they're spherical in shape. They're extremely porous, and they mimic kind of the environment that these denitrifiers are used to living kind of in the environment. So essentially from day one, when you load these biocatalysts in, you've got an extremely fast startup time. You've got an extremely high population of just pure denitrifiers inside of your reactor. So you're not dealing with competition from other organisms that you typically would come across. The sludge and the secondary waste is extremely minimized, and there are certain phenomenons that come into place that have been used in the pharmaceutical industry quite a bit. But when you take organisms and you put them in a confined environment, there are certain characteristics and changes that they go through, or certain processes that they'll try to avoid when they're in a confined environment. I can definitely expand on that a bit later. Footprint, reactor size, these are all smaller just due to the fact that you've got such a high concentration of denitrifiers inside of your reactor. So essentially you're able to do things at a much faster retention time, or what we call contact time. You get extremely high removal efficiencies. Toxicity tolerance is actually more applicable for our fermentation processes. So we can handle much higher toxic loads. It's much more robust. You also add some stability and some control to a biological process when you're able to control it on a micro level. So if I'm able to control it within my little biocatalyst, I have a number of distinct advantages rather than trying to control it in a 10 or 15,000 gallon type of reactor. The technology is disruptive in every kind of direction, especially from an operational standpoint. This was an economic analysis that was done with one of our clients who is now testing the technology. But from an operational standpoint, we did some initial pilot testing, and based on some of the initial pilot testing, we recognized reduction in chemical costs, big reduction in energy costs. Sludge generation was much less, and maintenance was less as well. When I talk about retention time is extremely important in biological system because it's a direct effect on the footprint and the size of it. And what I wanted to highlight in this specific slide is to touch on the number of different contaminants that we've come across, what the kind of conventional hydraulic retention times are, and what we've been able to achieve, just to show that the faster you're able to do, or essentially intensifying biological processes, you're able to reduce the footprint, and therefore you have a reduction in the capital costs. Now just to touch on the performance a bit, this one is actually an interesting case study This specific project was for some Aboriginal communities in Western Australia, and these are probably the most remote locations in the world. They're 6 to 8 hours from any kind of civilization. These Aboriginal communities, they're kind of the outbacks of Australia. They travel a lot, they move, they're very unpredictable, but they have essentially, they say naturally occurring nitrates in their soil and in their water. This was a project that was sponsored by the Western Australia Department of Housing. We went up against a reverse osmosis and ion exchange type system, and we showed that we were able to have much better economics, and it's much more suitable for these remote communities. Just to touch on, they had an influent concentration of about 100 parts per million. They wanted to get it down to 25. And one of the units has been installed, and the other unit is actually in startup type process. And the other thing I'd like to note is the microwave technology became the first biological system to obtain water quality certification in the country of Australia. So there's no other biological systems that are being used for drinking water purposes. The second one is actually, this was done at Sunny Slope Water Company in Pasadena. They've had a couple of wells that have been contaminated with nitrate, and essentially what they would do is they would buy clean water at $1,300 per acre foot, and they would blend it with the well that was contaminated, and essentially they would distribute it to people's houses. We did a small pilot study. This is a 5 gallon per minute pilot study just to show them that microwave can remove nitrate. The operation and the maintenance is much, much simpler. You had about 40 ppm going in. The target was just to get to less than 10 just so they can blend much more efficiently. We were able to get to less than 2 and non-detect. The retention time was 10 minutes, so the contact time was really, really minimal. It was easy to operate. We essentially had just a 1-day session with one of their operators, and he essentially operated for the 120 days. The purpose was to show that there's not a lot of training that's required to operate the microwave system. And based on some of the results, we were awarded a 10-year design, build, own, operate contract pending the CDPH conditional acceptance. This is just kind of outlining the performance that was achieved. You averaged about 35 parts per million of nitrate, below 10. Obviously, that was the goal that they wanted, so that was kind of the purpose of it. You'll notice towards the end we had a 14-day shutdown period. We shut down the entire system for 14 days, and within 24 hours it was up and removing nitrate. A key aspect of biological treatment is essentially you'd like to remove the nitrate, but you do not want to produce nitrite. And so this is kind of the nitrite profile as well. So if you get incomplete denitrification, you're going to produce nitrite, and so you've got to really monitor that and make sure that you stay below the MCL. This is a larger demonstration project. This is a non-potable water. It's a groundwater remediation site that has nitrate and perchlorate. It's 120 gallons per minute. The nitrate concentration is 10. It's got a really high perchlorate concentration, but this was to demonstrate at scale that we can essentially install a system and do a kind of a side-by-side comparison to an existing type system. This is located in Northern California and is available for a visit anytime. So this slide doesn't seem like it came out too clear, but essentially Eugene wanted us to put together a kind of an economic analysis on a 50 gallon per minute system that could be used in a rural community. 60 ppm was the design parameter as far as the nitrate concentration. I think we came out, these are just kind of ballpark numbers, but this is considering it's a continuous flow. So if it's not, you may have to have like a storage tank to store some water. The total capital cost came out to be around $220, with about 180 of it just being the system treatment cost. I was actually talking with David. There are certain things that are economies of scale, but there are certain things that even if you scale down, there's costs associated to them. So if I've got inline DO analyzers and nitrate analyzers, and I've got a PLC system, you're not going to see a big cost reduction whether I'm doing a 1,000 gallon per minute system or a 50 gallon per minute system. So there are certainly certain things that can scale down, but then it gets to a point where the cost really doesn't change. There's still a little bit of engineering and electrical and PLC type work that goes in providing some automation. Instrumentation as well. Instrumentation doesn't vary significantly whether I'm doing a 50 gallon per minute system or a 100 gallon per minute system. O&M cost, it came out to be around $21,000 a year. This includes an annualized biocatalyst replacement cost. We suspect that our material will last 5 years before needing replacement. That's still a big unknown. The 5 years is just what we've seen to date. It still hasn't failed, but there's a high, we just assume that every 5 years you'll probably need to replace it. And so you're probably looking at, as far as cost per 1,000 gallons, your capital cost, you're looking at 42 cents per 1,000 gallons, operating cost of 80 cents per 1,000 gallons, and a total treatment cost of $1.22 per 1,000 gallons. And that is it. So I'm open to any questions.
Thank you. Paul Boyer, work at Self-Help Enterprises. And question, you said that the footprint for the actual nitrate treatment system is relatively small. Now, how about the filtration and disinfection afterwards? Like, for example, could you estimate, like, for a well that produces 200 gallons per minute, that's just over the MCL of 45 parts per million, what the footprint would be for the total?
For the
treatment?
total?
Yeah.
And I probably wouldn't be the best person to answer that. And the only reason I say is that we really focus on the reactor itself. And the post-treatment, we typically have partnered with other people to do the post-treatment. So my understanding is the filtration and the chlorination or any kind of post-treatment that takes place is based on what's coming out of the reactor. So if I've got much less solids coming out, then I can design a post-treatment system that would be smaller. But I don't think I'd be the best person to kind of give you an estimate as to what a post-treatment system would look like.
One at the back.
Garrett Walker from the City of Angels Camp. But what, just a curiosity question, and I know you said you can't say, but what are they typically using as the filtration afterwards? What type of system are they using? So
we plan on testing this. We've seen in our systems, we haven't had any drinking water systems, but this is part of the challenge testing with the Department of Health. We've implemented a filtration system, like a regular sand filter, a multimedia filter, as well as chlorination. But what we'd like to do is we're trying to devise a process where we can eliminate the filtration system. And one of the unique ways that we're doing it is, this is kind of in process, and we haven't really talked to Eugene about this, but we are thinking about chlorinating the influent waters, so essentially eliminating any kind of indigenous bacteria that's in the influent water and then running that water through our system. Because the only time that we see any kind of turbidity or any type of growth is when over time you're going to essentially, when you're dosing a carbon with the influent water, which has a ton of indigenous bacteria, you're going to see some growth. And that growth is typically what needs to be filtered post. Nothing leaches out from the biocatalyst. There's no waste that's produced from the biocatalyst itself. It's essentially just a function of the overall process of dosing carbon to kind of an influent water stream. That needs to be then taken care of, or to be, able to reduce the turbidity. But we're looking at ways, for example, the projects in Australia, they have a UV they actually have a UV up front before our reactor, and that has, obviously that's a cost that's associated to that, but it saved them a lot from a filtration standpoint.
Jess Brown with Crowell Engineers. Two quick questions. One, you mentioned an electron donor is typically used. Is there a preferred? Is it usually acetic acid or ethanol? Is the first question.
Yeah, we've used ethanol and acetic acid.
And they both work about the same?
They both work about the same.
The second question is, you also talked about how different configurations can be used, packed bed, fluidized bed, CSTR. Is there a preferred mode of configuration for the media itself?
Yeah, what we've seen is it's actually very beneficial, specifically for nitrate, because you're producing such a high or a certain amount of nitrogen gas. We've seen that a kind of a fluidized bed reactor works best for nitrate applications, because then you don't get any of the gas, nitrogen gas that gets trapped in the bed. If you get gas that's trapped, you can lead to channeling and whatnot. So we've done fluidized bed reactors, but the big advantage to fluidizing, for example, the microbial biocatalyst versus like a carbon, is the biocatalyst is, from a density standpoint, is very similar to water. So it's very, very light, and it fluidizes very, very easily. So there's a lot of, from a pumping standpoint, it's much easier to really fluidize. So there's some pumping savings there as well.
Other questions?
Chad Seidel, Jacobs. I'm curious to know the population of nitrifiers that you use and if it changes over time. You know, the other systems that use, you know, indigenous populations that start after the initial startup and acclimation period, they change and evolve over time. Do you see the same thing happening in your instances? I was presuming this before you said about disinfection pre-reactor,
Right.
But if you could comment on that, I'd be interested to hear.
Yeah, we've run a lot of studies on, there's a certain chemical formulation that goes into place into creating these biocatalysts. So it's a very, it's a certain structure that we're trying to create at the end of the day. And so the amount that we, for lack of a better term, inoculate, there's certain percentages, and it changes from one application to another. We try to put a certain amount in there. It's not fully, it's just kind of, it's almost like it's seeded inside there. But it's enough to get the performance that you require. But what happens is, and we've noticed this, is that it'll grow to a certain population, and essentially the population will just stop because there's just no more room to grow. And it's a kind of a phenomenon that takes place when you put organisms in a confined environment and there's no more room to grow. They essentially begin using the nutrients and the electron donor or the carbon, not to grow anymore, but actually to degrade. We really tested it out in a fermentation process where we used yeast, and yeast is an extremely fast-growing organism. And essentially we have electron microscope type pictures from day 1 and day 600, and you'll see that after 30 days, from day 30 to day 600, you essentially see no growth from a population standpoint. And that's one big advantage, and that's one big concept that leads to production of sludge or excess biomass. So you're able to control the population.
Any other? Okay. There's one coming to you. While he gets up to you, I've been asked by those on the web to restate that the presentations can be found at www.drinc.ca.gov/DNN, and go to full agenda and you'll be able to see the presentations. I also need to tell you that Dr. Cohen's presentation will be posted later today. Go ahead, sir.
Hi, Ellie. Todd Webster, Envirogen. Can you talk about your biocatalyst itself? Is it NSF61 approved, or is it considered to be NSF60 approved? It's not really a chemical addition, it's really part of your equipment. So is it currently approved under NSF61?
Yes, just actually a couple weeks back, we got NSF61 certification on the biocatalyst.
Up to you.
And just to touch on that, the importance of that is that it shows that essentially nothing is leaching from the biocatalyst. So if water comes in contact with it and leaves, essentially there's nothing that's leaching back into the water. So that was kind of a big accomplishment for us.
My question is just about the capsules themselves and how long, just as a physical media, do they break down? Do they rupture? What kind of problems would you encounter in terms of the design of the capsule?
Yeah, can you
I'm
identify?
Stephen Klein with the regional board in Fresno.
Okay. Dr. Shirazi, our founder, it was kind of almost a 10-year. There's a lot of different types of materials that are used for these, and you'll see a lot in the pharmaceutical industry. The material that it's made of itself, if you leave it, essentially, if you leave it out in nature, it takes approximately 20 years for it to degrade. So it's a synthetic material. It's a food grade material. Our hunch is that, I mean, if you've got, we've seen like a stir tank reactor where you've got a stir in the reactor, you can cause shearing and you could damage the biocatalyst that way. The longest that we've seen them is 5 years. And they've been able to perform up to 5 years. We just don't know when the kind of the end game is. Hopefully it's not infinite, because then we won't be in business.
Okay, we do need to get on to the next presentation, so thank you very much.
Thank you.
So next I have nitrate treatment with Aeronite, a novel hydrogen-based biological reduction process. David Fries. Would you like remote or that?
I'll use the hand, I think. Okay. And do you want it here, or do you want me to put it back up on? Oh, it's okay. Yes, okay. All right, well, it's my pleasure to it's really an exciting time, because biological treatment's been a number of years coming, and we're really getting really close to having a number of large systems installed, including one of ours. And I get the pleasure to talk about another novel subject. I didn't cooperate with the prior speaker to use that word, but we've got another novel one. I'm sure we got some more. What's pretty unique about our system is that we're using hydrogen gas as our electron donor. I'm going to talk about how we're doing that and what